This is FRM Part 1, Book 2, Foundations of Risk Management, and this is Chapter 4, Bayesian Analysis. Let me tell you just a quick story. I was at a budget committee meeting at the school in which I teach, and we were talking about enrollments. And of course, lots of colleges have enrollment issues these days, and so we were talking about stuff that we can do to improve our enrollments for next year. And so in September, we start sending out stuff, and then we invite students to school, and then we accept or reject them, and then we invite them back. And, we have a series of things that we do. And I started thinking that this sounds an awful lot like some kind of a framework in which Thomas Bayes could help us. But the fascinating thing is that we're trying to figure out the probability that a student will accept and commit to our college given all the stuff that we do. Now, maybe that's not a good application and a perfect application of a Bayesian analysis, but it gives you a sense that over time we can learn from, it's better to do this to attract more of these kinds of students than it is to do that. Now, of course, today we have no idea how many new incoming freshmen that we're going to have next September, and so the interesting thing here is what do we know and how do we know it and how do we apply that? And so this shows up in these learning objectives here. So we're going to describe this Bayes theorem and do some calculation of conditional probabilities, and then we're going to compare the Bayesian to the frequentist approach. And so maybe a better example here than my budget committee example to compare these two kinds of approaches is the following. I wonder if you guys have children like I do. Remember, those of you who have been paying attention know I have these 14-year-old twin boys, and they lose their phone all the time. And so whenever they lose their phone, they look at their brother and say, "Hey, call me." And so the other one, calls that number, and so we listen for the buzz, or we listen for the ringing. And so what the frequentist approach will do is the frequentists will they will listen for the buzzing and then try to find it based on the buzzing. They do this frequently. They go to this room and that room and this room. They're trying to get closer and closer, kind of like that, you're getting warmer and you're getting closer game that you played when you were kids. But the Bayesian approach would absolutely listen for the buzzing, but the twin who lost the phone will say something like, "You know what? I've lost my phone 17 times when I was in my bedroom. I lost it 16 times when I was in the basement. I didn't lose it any times when I was in the bathroom." And so using that information, the given part, using that information to try to get to the phone faster. So we're going to compare those two approaches. And then we'll do two or more possible outcomes. All right, some opening remarks here. Suppose we have estimated prior probabilities for events that we are concerned about, and then we obtain new information, kind of like my budget committee conversation, in which we send out all of these acceptance letters, and then we kind of wait for them, and then they trickle in, and each time they trickle in, we can get information about those students who decide to accept our invitation to join our school. All right, then what happens, we would like to develop a sound method to compute revised or posterior probabilities. So the more we learn about those students who accept our invitation to attend our college, then the more likely that we'll be able to predict that final outcome. And so this is what Bayes' theorem provides for us. It's named after this dude, Thomas Hayes, who lived in the 1740s and 1750s and 1760s. He was actually the son of a minister, and he became a minister as well. He was an English statistician. So what it does, it helps us use a known outcome to predict a sequence of events leading up to the outcome. That's why I said that my budget committee and enrollment conversation is probably not a really good application of Bayes, because we don't really know how many students are going to show up in September. But nevertheless, that process helps us understand. So the terminology is to use this thing like a turnaround probability, and I'll show you what that means here in just a few slides. But what we do is we gain more information as we go through the process. Let's take a look at an example here. Let's suppose that you're fairly clueless about politics, and so you don't know who won the last presidential election, but you know there were two candidates, a Republican and a Democrat. But what you do know is that a tax cut was recently enacted, and you ask yourself, boy, does that sound more like a Republican or does that sound more like a Democrat? And so you have to figure out which one is the president. Is it a Republican or a Democratic president? So you look at some historical data and you figure that the probability of a Republican president completing this tax cut policy is 80%, whereas a Democratic president would only be 20%. So can these probabilities help you determine the probability that the sitting president, given that a tax cut was recently enacted, is a Republican or a Democrat? And then, yeah, Bayes' theorem helps us do this. What do we know? We know the probability of a tax cut given that the president is a Republican or a Democrat. But what we want is the probability that the president is a Republican or a Democrat, given that there has been a tax cut. So we know there has been a tax cut. We don't know which party the president belongs to. How about a financial example here? Let's suppose that you know the probability of a certified hedge fund manager earning an excess return or outperforming the benchmark, assuming the market portfolio is X%. You also know that the probability of a non-certified manager earning an excess return is just Y%. All right. Now, if you know that a manager has actually earned an excess return, so you just randomly pick a manager and this manager has generated an excess return, can you figure out that what the probability is that the manager is either certified or non-certified? And the answer is, of course, yes. So what do we have? We have the probability of an excess return given that the manager is either certified or non-certified, right? But what we want is the probability that the manager is certified or not certified, given that what we know, there has been an excess return. Let's take a look at a simple case here. So here's the Bayes formula. On the left-hand side of the equal sign, we have the probability of event A given that event B has occurred. That's called a conditional probability. And that's equal to, on the right side of the equal sign, we're going to take a ratio. The probability of B given A, this is also a conditional probability, but this is taken from the data. We also have in the numerator the initial belief of probability A occurring. We call that a prior probability. And then we have to divide by the probability of event B. And what that does is it forces the probability distribution to sum to 1. All right, let's take a look at this in a little bit more detail. And so note, what do we know about conditional probabilities? The probability of A given B can be defined as the intersection of A and B divided by the probability of A. That's what I have at the top left there. And then the opposite of that is the conditional probability of B, given that A has occurred. And so notice that in the numerator there on the right-hand side up at the top there, I have the intersection of B and A divided by the probability of A. Now, of course, what we know, this intersection A and B and A, they both mean the same thing, right? Think of, those sets that you have when you're in the 5th grade or whatever. And so intuitively, A and B and A are identical. All right, so I can put that equal sign there, and then I can do some substituting, and I can do just some cross multiplying, and I can deduce that. Notice I have those arrows there pointing up there, and so that's just showing you where to cross multiply. And so we can get that formula there, and then we can divide both sides by B, and that gives us our Bayes theorem. So what I have in the blue box there is the same thing that I have in the blue box there. Now this is the simplest case, and so let's take a look at it at an example here. You guys know I like to give sports analogies and sports examples. Given the fact that I still have not started my tax return in the however many days it is before April 15th. Let's suppose it's April 15th. You file your tax return at 8 o'clock and you're rewarding yourself by going out to play golf. And so you look outside and you see a cloudy sky. You want to play golf today, but you know that April is a rainy month wherever you live. And so let's just suppose that it on average, it rains every other day in April. Now you know that 60% of cloudy days will end up being rainy days. And you also know that 45% of all April mornings are cloudy. All right, so here's our question. What is the probability it will rain during your round of golf, given that today, April 15th, it's a cloudy day? All right, so what do? We start with the probability that it's going to rain given clouds. So what do we know? What do we know here? That it's April 15th, right? April has 30 days. So if it rains every other day, so I guess I'm just assuming they're 50%. So we're going to multiply that 50% by the 60% chance that cloudy days will end up being rainy days. And then we're going to divide by the 45% because all April mornings are cloudy. I'm sorry, 45% of all April mornings are cloudy. And so that gives us a probability that it's going to rain during our round of golf today on April 15th of 67%. And see how this Bayes' theorem adds to our understanding, because just a simple application of this, of some simple statistics would be that April is a rainy month, it rains every other day, so you would think that we have a 50% chance of being rained on today, right? That's just a simple deduction. However, we have some more information. We have the information about cloudy days and the relationship between clouds and rain. So we use all that stuff to refine our estimate of the probability of rain from just a simple, naive 50% all the way up to 67%. Now, this can be applied over different sets of probabilities. So there's the general Bayes theorem, the general case in which we can do this for I equals 1 and 2 and 3 and 4 and all the way out to n. Now let's make sure we understand the difference between these prior and posterior probability. So the prior probability is the probability of an event before new data is collected. You know, like let's go back to my sons losing their phone. The probability of them losing their phone is 100%, but the probability of them losing their phone on any given day is clearly not 100% because they haven't lost it 100% of the time. The probability of them losing their phone today depends on how many hours they play Fortnite, how much homework do they have, are they going to basketball practice, et cetera, et cetera. All right, so notice what I have there in that first bullet point. It's the best rational assessment of the probability of an outcome based on existing knowledge. But then a posterior probability is the revised or updated probability taking into consideration new information. So if my boys if they're playing Fortnite and they have basketball and they have homework, who knows what's going to happen to that phone? All right, so we start with the prior probabilities, then we gain the new information, then we apply the Bayes formula like we did in the golfing example, and then we can come up with these posterior probabilities. How about going back to our previous examples here? A priori probability would be the probability that the president is elected is Republican, or the probability that he or she is a Democrat. A posterior probability would be the probability of a Republican president, given that there has been a tax cut. Let's go ahead and do some more math here in example 3. All right, let's suppose we have a consulting firm bidding for a consulting contract. So the firm's management feels that it has a 50% chance of landing the project. However, the client to whom the bid was submitted subsequently asked for additional information. All right, so there's that 50% chance, but now the client has asked for more information. Well, clearly, more information about whatever the client wants information, that can help us refine that probability. All right, so from historical data, we know that a client asked for additional information for 70% of successful bids and 40% of unsuccessful bids. So what is the posterior probability that the bid will be successful given a request for additional information? So we can put together a matrix there. So down the left-hand column, we've got the event, successful, which means obtaining the contract, unsuccessful, which would mean a rejection of the contract. And so the probability of an event, 50%, right? We go back here, we have 50% chance of landing the project. And then the probability of additional information is 70 and 40. And so all we need to do is apply those probabilities into the numerator and to the denominator, and that refines us back up to a 63%. Because what do we know back here? Given a request for additional information, and so you're tempted to jump that up to 70% right, but it doesn't quite go there. It goes to 63%. How about another example? Suppose you are an equity analyst and you use historical data to categorize managers, portfolio managers, as being either excellent or average. And so you have some rubric where you put them into one of those two categories. All right, now let's add some more information. 20% of fund managers are excellent and 80% are average. So the probability of a manager outperforming the market in any given year is independent of their performance in any other year. And by the way, that's been shown by lots and lots of financial research, is that historical outperformance for mutual fund managers really doesn't actually predict future outperformance. In fact, some studies show just the opposite, that outperforming managers tend to underperform. Maybe that's an application of reversion to the mean. All right, so let's take a look at a new fund manager, which started 3 years ago, and this fund manager outperformed the market all 3 years. So what is the probability that the manager is excellent? All right, so let's put together that table. We've got down the left-hand column, excellent and average, and there's the probabilities, 20 and 80, and then probability of beating the market. And so let's go ahead and just apply those probabilities into the numerator and the denominator. And then remember that when you do this series of steps, we're going to do this over 3 years, so we need to raise it to the third power, and that just goes back to a simple application of like those old time value of money principles when you're compounding, and when you do the same thing with probabilities, you got to multiply those probabilities. So raise those probabilities of beating the market, so 1 and 2 and 3 years, raise it to the third power. So that gets us up to 57%. How about the Bayesian versus the Frequentist approach? So let's go back to my sons losing their phone. The Frequentist approach involves drawing conclusions from sample data based on the frequency of that data. All right, so if the sample data consists only of observations that are positive events, then the probability of a positive event will be 100%. Right, so you look in the blue box there. You have a +1 and a +6. So all those are probabilities. All those are positive numbers. And so notice I got the dots after the +5. Whether there are 5 or 500 or 5 million of them, if they're all positive, then the probability of a positive event will be 100%. Swinging back to that example that we just did on the previous slide, if a manager has outperformed the market in each of the last 3 years, the Frequentist approach will say that the probability of this manager outperforming the market next year is 100%, and that's based on just a three-year sample. And so the Frequentists, what they do, that's what their name says, the frequency of that data, they rely on the frequency to make conclusions about the future. So here's a good slide here. The primary difference between the Bayesian approach and the Frequentist is that the Bayesian approach is based on a prior belief regarding the probability of an event occurring. Now remember, when that what the frequentists will do when they hear my son's phone buzzing is they don't care if my son ever lost his phone ever before. And they don't care where he lost his phone before. So they could be looking over there and over there and over there. They're just going by the sound of the buzzing. All right, so frequentist never uses or gives probability of a hypothesis, does not require prior, and it tends to be less computationally intensive. Now, of course, that's why I put this, here, let me show you this, the bottom box there, that illustrates that a lot of opponents will say, how can you conclude that this mutual fund manager has a 100% chance of beating the market just because it has a small data set? And I think that takes us through the learning objectives for this chapter. Be sensitive to the learning objective action words or command words. There you have a describe and a compare and an apply. So that probably means that you're going to have to do some computing or some calculation. And by the way, you'll probably have to do some calculations as well if the action word says something like distinguish. We don't have one of those distinguishes here. Maybe even an explain or demonstrate. So you probably should be aware of the math, even though it might not sound like it.